In 8.3, we're going to do a different kind of integral that deals with different combinations of trig functions. Just to review, you've got to remember, because you're going to use these a lot, the tangents is sine over cosine, cotangents, cosine over sine, blah, blah, blah. You know all these. Pythagorean identities, the main one, sine squared plus cosine squared. You're going to be using this a lot in all of its other forms. For instance, sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared. You're going to be replacing cosine squared with 1 minus sine squared, vice versa. Now, if you take this basic one and you divided everything by, let's say, cosine squared, sine squared over cosine squared is tangent squared, plus 1 equals secant squared. So you get this new form of the Pythagorean identity. Remember now, secant squared minus 1 will be tangent squared. If you divide all of this by sine squared, you'll get 1 plus cotangent squared equals cosecant squared right here. And you'll also use things like cosecant squared minus cotangent squared equals 1, or more likely cosecant squared minus 1 equals cotangent squared. Another thing that you're going to be using a whole lot, so it's very important that you remember, is the power reducing formulas. You're going to use these when you're integrating, because if you happen to have the integral of a sine squared or a cosine squared, and that's all you have in your integrand, then you have to replace it with this. It's kind of the form, two different forms of the cosine of the double angle. And this is easy to integrate. This is impossible. So you have to use these identities. To start off, let's talk about integrals that involve sines and cosines only. Remember that the derivative of the sine is the cosine, but the derivative of the cosine is minus sine, okay? So they're each other's derivatives with just one SIGN issue going on. So if you have a product of a sine and a cosine, and they're to two different powers, then you're going to have to figure out how to create a perfect derivative using just those two factors. So if either power on the sine or the cosine happens to be odd, then you need to factor one of those. It doesn't matter which one. If they're both odd, you can pick. But if either one of the powers of sine or cosine are odd, you want to factor out that function to the first power, leaving behind that function to the even power. Even powers of sines and cosines can be reverted back using the Pythagorean identity to the other function, okay? So you want to pull out that function to the power of 1, leaving the even power behind, and use the Pythagorean identity to change what's left so that you have a single factor of sine or cosine to the first power. Everything else can be changed to the other. Okay, let's look at this guy right here. We have sine squared, but cosine is an odd power. So I factor off a single factor of cosine, which leaves me with a cosine squared. Recognizing that cosine is the derivative of sine, then we can use the Pythagorean identity to change this cosine squared to be in terms of the sine squared. So we have 1 minus sine squared, that was the cosine squared. There's the sine squared that was already there, and here is your cosine. Why are we doing this? Because we want to have a function of sine and set sine equal to u, and this will be our du. So when I take the sine squared and I distribute it, I'm left with sine squared minus sine to the fourth. Each of those gets this cosine, and you see that I have u to the 2 du minus u to the 4 du. So the point is you factor off cosine to the first power, leaving an even power behind. Use the Pythagorean identity to get all of the integrand in terms of the sign except for this single cosine. This will be your du. And look, your function that you're integrating is going to be u squared minus u to the 4th du. Simple power rule integrals. Even though it's got all of this mess in it, it's very simple. You're integrating u squared du minus u to the 4th du. Okay, I've said that enough. Here's your answer. You just added 1 to the power divided by the power. Where did the cosine go? The du always gets used up when you do the antiderivative. Now notice that in my answer, I got a common denominator, factored it out, and I pulled out the lowest factor of the sine. That gave me sine cubed over 15. I had multiplied this by 5 over 5, so I'm left with a 5. Minus, multiply this by 3 over 3, and there's a sine squared left in that one. Check your work by taking the derivative of this. It's a single product rule here. Instead of doing 2 chain rules, I'm going to do this product rule. Okay, in this case, both sine and cosine are odd, so it doesn't matter which one I choose to factor out. If I choose to factor out a cosine, the derivative of sine is positive cosine, so I have no adjusting left to do. So I factored out one of these, that left 4 of them. Well, this is just cosine squared squared. So I changed cosine squared to 1 minus sine squared. He's still squared. This has to be FOILed out like this. Then I'm going to distribute the sine to the 5th and get this. Now this is u to the 5th minus 2u plus u to the 9 du. Okay? So you just add 1 to the power, divide by the power, all the way through, make it simple, get a common denominator and factor out the lowest power, make a list of what's left. It's really very simple if you practice. Now remember I said that if they were both odd, you could choose whether to factor out a sine or a cosine. On the previous page, I factored out a cosine. This time, let's factor out a sine. That leaves us with sine to the 4th, which is sine squared squared, and sine squared is 1 minus cosine squared. So there you have it to the 4th. FOIL this out, boom. Take this cosine to the 5th and distribute it here, boom. So I have u to the 5th minus 2u to the 7th plus u to the 9th du. That's the whole point of factoring out the sine or cosine to the first power. He becomes your du. You get everything else in terms of the other function, so you have a power rule function in terms of your chosen u. Now in this case, the du needed a minus sign, so we multiply by minus on the inside and the outside. He stays on the outside. Do your power rule integral, simplify and factor, make it pretty. Next topic. Let's say we have products of secant and tangent. Now secant and tangent are kind of in a family because they have a common denominator. They both have cosine in the denominator. So we're going to be talking about products of secant and tangent to different powers. Now remember the derivative of tangent is secant squared. So if I can pull out a secant squared, then that will be the du if my u is tangent. If I can factor out a secant tangent, that will be the du if I have everything in terms of the secant. So these are best learned by just doing them. Play around with them, and then you don't have to remember these rules. But for now, if the power of secant is even, factor out secant squared and change the rest. If it started as an even and you factor out a square, the rest will be even you can use the Pythagorean identity to change the rest to tangents, okay? If the power of tangent is odd, then you can always factor out a secant tangent. That will leave you with even power of tangent, which can be changed from tangent to secant. All right, so some examples. Secant to the fifth, tangent to the third. Both of these are odd, so I'm going to factor out a secant tangent. That leaves me with even powers. Secant tangent is the derivative of the secant, so I want all of this to be in terms of secant. Tangent squared is secant squared minus 1. Pythagorean identity. Plug that in, distribute the secant to the fourth here. I end up with u to the sixth minus u to the fourth. There's my perfect du. So it's just a power rule with respect to the secant function. So I've got secant to the seventh over 7 and secant to the fifth over 5. Common denominator, factor out the lowest power, boom. Now in this problem, the secant is even power. If I were to pull off a secant and a tangent, I'd be left with a secant. That was an odd power, and I couldn't translate this into being a tangent. So I'm going to pull out 2 of these. So secant squared is now my du. That means I want all of these to be tangents because secant squared, is the derivative of the tangent. So pulling 2 from here leaves me with 4. This is secant squared squared. Secant squared is 1 plus tan squared. I have that squared. I have to FOIL this out. Then I'm going to distribute the tangent to the fifth. And when I FOIL this out, I have 1 plus 2 tan squared plus tan to the fourth. So distributing gives me tan to the fifth, 2 tan to the 7 plus tan to the ninth, and this is the derivative of the tangent. So I'm just going to add 1 to the power, divide by the power for each of these terms. That gives me this. Cancel where you can, and then I got a common denominator, which was 36, and I factored out the smallest power of tangent, left me with this. Okay, now if secant has an even power and tangent is odd, you can choose whether to factor out the secant squared, because you'll be left with an even power, or to pull out secant tangent. So let's look at this problem right here. I see I can pull out a secant squared, I'll be left with secant to the fourth, which can then be converted to all tangents. Or I can pull off a secant and a tangent. That's going to leave me with an even power of tangent, which can be changed to secant. So we're going to try both. And first, we're going to try pulling off a secant tangent. That is the derivative of secant. So I want all of these to be secants. So I'm left with pulled 1 out, right? So I'm left with secant to the fifth, pulled 1 of these, that's tangent to the fourth. Well, tangent to the fourth is tan squared squared. So tangent squared is secant squared minus 1. I missed an x there. And this is secant squared, tangent squared squared. So this has to be FOILed out. Let me make a little note here. This will be secant to the fourth minus 2 secant squared plus 1. And we're going to distribute secant to the fifth through there. I'm going to run out of room here. Hold the phone. Messed a lot of stuff up, so we're fixing this. All right, secant to the fifth times secant to the fourth. Secant to the fifth times secant squared, so I have minus 2 secant 7. And then I'm going to have secant to the fifth times 1, so plus secant 5x times secant tangent. So this is the derivative of the secant. So this is the du. I have u to the 9 minus 2u to the 7 plus u to the fifth du. So it's just a power rule integral, and I'm going to get secant to the 10 over 10. The next term is going to be minus 2 secant to the 8 over 8. I can cancel the 2 with the 8 and get minus secant to the 8th over 4. Then I'm going to have plus secant to the 6th over 6 plus c. Common denominator will be 60, and I can pull out secant to the 6th, and I will be left with 6 secant to the 4th minus 15 secant squared plus 10 plus c. Fun stuff when you get the hang of it, but practice, practice. The next thing we're going to talk about is very important, power reducing. Remember I told you you can't just take integrals of just the square of sine or cosine. Same follows for to the 4th. So for the sine squared, we reduce it using a form of the cosine of the double angle. Let me write that down real quick. Cosine of 2x is it's cosine squared minus sine squared. But if I replace the sine squared with 1 minus cosine squared and distribute the minus, I get 2 cosine squared minus 1. But if I had replaced the cosine with 1 minus sine squared, I would have gotten 1 minus 2 sine squared. So using these formulas for the cosine of the double angle, these two, and solving for the cosine squared, I would add 1 to both sides and divide by 2. That's going to give me this formula right here. Cosine squared is 1/2 plus 1/2 cosine of the double. This guy right here, this guy, if I had isolated sine squared, I would have subtracted 1 and divided by a negative 2, which would make the 1 positive and the cosine of 2x negative. So sine squared gets replaced with 1/2 minus 1/2 cosine of the double. So you compare these two formulas and you see they're exactly the same, except this one for cosine is addition, for sine is subtraction. But this is easy to integrate, right? So if you have sine squared, replace it with 1/2 minus 1/2 cosine of 2 theta. This is just, or 2x. This is 1/2 x, simple integral. This needs a du of 2, so you're going to multiply by 2 and divide by 2 and get the 1/4. And the integral of cosine is the sine. For this one, it's the same answer, it's just a plus. Now, if I had cosine or sine to the 4th, I could say that in this case, it's cosine squared squared. So I replace cosine squared with the power reducing formula, but that is then squared to make it to cosine to the 4th. I have to FOIL this out, so I get 1/2 times 1/2. Then I'm going to get 1/2 times 1/2 cosine, which is 1/4, plus another 1/2 times 1/2 cosine, which 1/4 and 1/4 is 1/2. And then this times itself, which gives me 1/4 cosine squared. This is an easy integral. This is the substitution integral. I need a 2. I divide by a 2, gives me a 4th. Integrate the cosine and get sine. But this guy right here, I'm going to factor out the 4th, and I'm going to integrate cosine squared. Well, cosine squared has to be replaced with 1/2 plus 1/2 cosine of double this angle. So now I've got a cosine of 4x. Remember, it's not just about these angles being 2, all right? It's about these angles being twice what I started with. So if I started with a 2x here, where's my integral? If I started with a cosine squared of 2x and I use power reducing, now it's double 2x. Again, this is 1/8 and I integrate and I just get an x. This is 1/8. I need a 4. I've got to divide by a 4. It's going to give me 1/32. So, and the integral of cosine is sine. So this is your answer. It's ugly, but it is what it is, right? We also have 1/4 x and 1/8 x that can be put together to be 3/8 x. Now, if you have a product of sines and or cosines, in other words, sine times sine, cosine times sine, cosine, or a mixture of sines and cosines, but your angles are different, you must use an identity. You can't do what we did on the first page, where you factor off one of them. If they're different angles, they can't be the derivatives of each other. So you have to do something different. In this case, you have a product and you want to change it to a sum, and that makes makes it much easier to integrate it. So if you have the product of two sine functions with different angles, the formula says that it's 1/2 times the cosine of the difference in the angles minus the cosine of the sum of the angles. Cosine times cosine with different angles, 1/2 cosine of the difference plus cosine of the sum. You see how these are very similar? Everything's the same, except for if I started with sines, I have subtraction. If I started with cosines, I have addition, just like you did with the power reducing. Now, if I have a combination of sine and cosine, then my answer, my formula to replace it, the sum, is going to be 1/2 sine of the difference plus sine of the sum. So notice that when the functions are the same function with different angles, we have all cosines in our formula. The product of sines gives me subtraction. Product of cosines gives me addition. But if I have a mixture, I have a mixture of sines with addition. Okay? These formulas come from the formulas for sine and cosine, the sine of the sum and the sine of the difference and the cosine of the sum and the cosine of the difference. You can find those in any trig book, and I'm sure they're listed somewhere in this section to show you how to formulate these formulas. So you don't use them very often. So in reality, when you do need them, you'll be able to look them up. This example right here, we have cosine of a 3x and sine of a 1x. So you see it's a mixture of sine and cosine. We're going to use this formula. So my answer is going to go from the product of cosine and sine to the sum of sine functions. The first one is the difference in these angles. And notice I wrote 1 minus 3 because it had m and n up here. So I replaced this product with the sum, 1/2 plus sine of the sum. All right, this is very simple, two separate integrals now. I'm integrating just the sine. Now, one thing to remember, the sine of the negative angle, let me draw a little picture. You have your circle here. If I rotate this way, to this angle, alpha, I have a particular value of sine. If I rotate this way, the same distance where these things match up, right? I'm going minus alpha. Notice that I'm going to get this, my circle is crooked, but I'm going to get the same value of sine. It's just the negative of it. It doesn't matter how far around you rotate, but when you rotate in the opposite direction, you get the opposite value of sine. Cosine, you get the same value because the cosines will match up. But this is actually just negative sine of positive 2x. So when I integrate this, I need a 2, which is going to give me a 4. Another 2 here gives me a 4 in the denominator, and the integral of negative sine is positive cosine. Here I need a 4, so I'm going to divide by a 4. That gives me an 8, and the integral of sine is negative cosine. And when you just can't figure it out, and none of the formulas work, and you don't know what to do, you can always fall back to changing everything to sines and cosines, use your identities, and you'll be able to figure it out. So look at this example right here with cosecant and cotangent in the denominator. Well, cosecant is 1 over sine, cotangent is cosine over sine. So this gives me in the denominator cosine over sine squared. 1 over that flips it upside down. So now with this guy right here, what are you going to do? I chose to use a Pythagorean identity to replace the sine of x on the top and make it 1 minus cosine squared. Now we have a single cosine in the denominator. This is looking pretty good. 1 divided by cosine is secant. Cosine squared divided by cosine is cosine. The integral of the secant is the ln of the secant plus tangent. The integral of the cosine is the sine, and it's subtracting. So it looked awful, but it's doable. Look at this one right here. I have no idea what to do, so I changed secant to 1 over cosine. And now looking at this, I don't like having a fraction inside my fraction, so I multiply the top and the bottom by that denominator, whatever it is. Now this cosine is going to get distributed to both of these pieces on the top. And remember, it was the top that I was messing with, okay? So I'm going to choose to leave the denominator factored, and you'll see that it plays out in a minute. Take this cosine and distribute it to each of these pieces. I'm going to get the cosine minus 1. When I multiply here, the bottom cancels, which was the main reason I was multiplying by it in the first place. So 1 over cosine times cosine gives me a 1. So now I have cosine minus 1 on the top and 1 minus cosine on the bottom. That's going to cancel out and leave me with a minus 1. And now I'm integrating minus 1 over cosine. So it's negative secant. And we know the integral of the secant is the ln of the secant plus tangent. And I have that minus sign going along for the ride. And I am done.